We start up again. Another equation, another problem. You light a match. Then what happens? You get a ball of fire expanding to some limit, and then he will stay constant. So we have a cute little model for that. The change time derivative of the radius y, it's a balance between the surface and the volume, something like that. So I want to solve that differential equation, finding the radius as a function of time. And according to theory, he should level off when you sort of have a balance between the surface and the volume of this ball. The problem is initial value. You have to start with something, and this model breaks down if you start with 0 when you ignite the match. You have to start with a small little ball of fire. So this one is a tiny little delta. That should be it. So another code. Clear all, close all, CLC, and we save that one as flame. So it's a very simple equation. Delta, what did I try with? Some small number here. Then we need some time step. I don't know, something like that. And then initial value y equals delta. That should be it. Let's try first the crude Euler for time equals 0, step delta t up to whatever, I don't know, so maximum time. And then we write this one on the form the new y equals the old one plus time step multiplied with, and then here we have now the right hand side of the equation system, which is y squared minus y to the power of 3. That's it. Plot ty, and then that should be it. Not exactly. If you do this plot sentence, he will give you one dot on the screen, and then he create a new figure for every time. So that doesn't really help. Figure 1. Hold on. Hold off. Something like that. Let's see if this one runs. It didn't seem to be much there. So let's try it again. I think I have to give in an initial plot. Plot 0 and y. And I also maybe should give him some bigger dot. Big O. Let's see if that helps. Yeah, something happens at least. Okay, goes like a straight line. Wasn't that a little strange? If we continue, how far should I go here? Shouldn't go that far. Let's try with a smaller delta. Yeah, I get the same value, fairly constant. Wasn't that a little strange? Even smaller. Yeah, but I get this different value for every time. I mean, this y seems to be fairly constant. A little strange. Let's see what we did here. Now it should be okay, I think. Yeah. So we have an equation behaving a little bit strange. Now if we try a smaller time step, yeah, let's see if he runs. Sort of gets different values every time, whatever you do, and seems to be just in a straight line. He's behaving rather peculiar. So when this happens, then what do you do? I mean, the equation system is fairly easy, isn't it? There shouldn't be any problem with that one. Let's try to find a solution here. An analytical solution. If you have the entire MATLAB, all packages installed, then you have something called a Symbolic toolbox, which is capable of doing analytical calculations for you. Not with numbers, not numerical, but analytical. Symbs, meaning now this y is a symbolic object. And then I write y equals dsolve. Dsolve, that is differential equation solution system, analytical. What should he solve? He should solve the derivative of y equals y squared minus y cubed. And then with the initial value y of 0 equals delta. Like that. So that one should now actually print out the analytical solution. Let's see if that one works. We can skip this one. There you have the analytical solution. Looks a little bit messy, doesn't it? So what can you do to remedy that? You have something called simplify. Simplify y, and then you can do this one many times if you like. Run this one. This simplify function, well, here I run it 100 times. It didn't change much. If you run it 1,000 times, well, it doesn't help. You have another option as well. If you don't like this, the printout, I mean, this one is written in MATLAB syntax. We have something called pretty y. Then you can get it on a form more readable. So this is the analytical solution to this cute little differential equation. I guess all of you know the Lambert W function, of course you do. No? That's strange. So we have actually an analytical solution. Okay. Let's go back and see. I can write this one here. Pretty y. This symbolic toolbox can actually be pretty handy if you want to just to check your answer, if it's possible to find an analytical solution. MATLAB is not the best. If you really have algebraic troubles, you fire up Maple. Maple is very strong when it comes to to handling analytical calculations. But the toolbox in MATLAB, it's okay. He can do at least some complex calculations for you. So I just comment out this one. We don't need it anymore. Then I believe I had the analytical solution. I wrote it like this: A equals 1 divided by delta minus 1. And then y analytical, that was 1 dot divided by, and then this Lambert W function is actually programmed in MATLAB, so you have a function for it. So it's an 17th century mathematicians called Lambert that invented it. What else did I write here? It was a exponent of a minus t plus 1. And then we can plot t versus y analytical, and that one, yeah, just plot it like that. Going back to t here, then I have to create something here, 0 delta t up to 10. Let's see if that one works. Yeah. So I have something here, and then I have something here. First order Euler scheme, he has really problems. Let's see how the solution, what it should look like. I still have the 0, can't have that one either. Still 0, how come? That shouldn't be correct, should it? Over delta, of course. It's actually correct. Because I need a time scale here, which is somewhat small. Let's see, linear space. Start from 0 up to delta, up to actually 2 divided by delta. And now see what happens. There we go. So this is actually the analytical solution. You start with a very small value for this very small delta, and then nothing much happens. All of a sudden, a lot of things happen. So this equation system, not so easy to solve for poor first order Euler. Say bigger delta. It helps. It sort of smoothen down the sudden jump a little bit, but you see it's quite violent. And point 1. Finally, that one is something that our Euler scheme should be able to handle. He should be. Let's try it. So we should go all the way to the time scale 2 over delta, but you see my time step has to be quite small. That was maybe a little bit too small for this computer. Oh yeah, he's taking forever. Let's kill him. Yeah, go away. So now, yes, he's actually capable of finding it. You see the red one in the center, but he needs many, many time steps to actually do this. And he's quite slow. If I change the delta here a little bit, then I have to change the delta t as well. No, let's try without it, see what happens. Oh, it's going to take forever. So this problem is nasty in the sense that it's what we called a stiff problem. We don't have any good definition of stiff equation system, but say stiff, they are not easy to handle. Typically they have slow, nice motion, and then all of a sudden some violent behavior over a very short time period. That would be typically a stiff behavior that numerical schemes will have quite a problem with handling. So here, this sudden jump, of course, you need very small time step just in this region to resolve this. For this area and this area up here, that shouldn't be a problem. There you could probably use pretty big time steps just in those regions. But when this sudden jump occur, you need some really fine time steps. Then of course our first order Euler code, it's not good anymore. So we remove it, and we remove this one as well, and this one, like that. I don't need that one either. Solve it using ODE45. What was ODE45? You obtain the solution from ODE45. You get a timetable, all the time steps that you have used where you find a solution. You get the matrix with all your unknowns. Here I only have one single unknown, so this will be just a single vector, one y for each of the corresponding times. ODE45, like that. And inside here I now need a function. Normally you will write an external file. Here I use an internal function, an inline function f. Then you need the time span, and the time span should then go from 0, and that was all the way up to 2. No, I don't think he can do that. T max, and then the initial value for y, that was delta. Maximum time, that's 2 divided by delta. That's a good time scale for this problem. Now I have to define this inline function f. So one way to do it, f equals inline. So now you can define it as, what was it? It was y square minus y cubed, like that, and then the variable was t, and then the other one was y. That one should actually work. So now if this one succeeds, I have a timetable t, which I now insert into my analytical solution. So in my plot sentence now I have t y and t analytical. For the numerical from UD45, I want to have say a line and a plus sign, so I can differ between them. Let's try that one. Yes, he can handle it. And he doesn't work actually too hard with it, and he gets a quite good agreement. Big time steps, and then he see something is happening here, he needs to use smaller time steps, and here he really works a lot, but he can do it. Now the delta I used here, it's fairly big, so now we start to squeeze him a little bit. 0.001. He can still do it, but you see he's really struggling. So if we zoom in here, oh yeah, he has trouble finding the correct solution. But he does the job. So you might say stiff equations, they are really not a problem if you can afford the time. The ordinary methods will solve stiff problems. They just use a heck of a long time to solve it. 3 zeros. Okay. And then you can continue and continue and continue. How about 4? Can you do it? Reads down here, busy. So if you are wondering what's going on, check if you have the busy here. And if you are getting bored, click on the command window, Control C, then you kill, hopefully you kill the code. Yeah, how much should we give him? I think we forget it. 4 zeros, that was too much for him. But he handled 3. He could take 3, at least for a reasonable amount of time. He will take 4 as well, but he's going to take a very, very long time. And if you try with 5 and 6, just forget it. He's going to stay forever. And you see he's really, really working here. This is not an easy task for him. So what do we do now? I want to have a much smaller delta than only 3 zeros here. What do? You ask the documentation, doc UD45. And then someplace down here you should find yeah, choose an UDE solver. Maybe we have a choice here. Should be a list here somewhere. Here we go. UD45, that's sort of the first one you try. That's the workhorse in MATLAB. 4th order accuracy using a 5th order method. Very advanced, but non-stiff equation. And you can squeeze the accuracy, if you like, to higher than medium. But as it says, most of the time, that one is the one you start with. If you are not so interested in accuracy, you can try these, 23 or 113. They are, can be more efficient, but then the solution will not be so good. We can try with 23 just for fun. So what's nice then with the different UD solvers, you just have to change the name. The setup, everything else is identical. So I can run this one. Yeah, I get the same roughly, a little bit faster maybe. But here you see he sort of misses the jump a little bit here, and also quite violently. It's not a good solution, that one. So then, okay, we acknowledge our problem is stiff. 15s. That is the one to try if you have suspicion that, yes, I have a stiff problem. 15s. And run. There you go. Yeah, he missed a little bit, but at least he is fast. And he doesn't use that many steps. So he's quite economic. Now we can try to squeeze him with 4 zeros. Still misses, but he's fast. 5 zeros. Oh yeah. So seems to be doing the job, although he really misses the jump, doesn't he? Okay, how can you remedy that one? It's a good method. I mean, he's fast, but he doesn't do it quite correct. So possible then should be to use some options here. For ODE set, there you can change the default inside the ODE solvers, and you have something called relative tolerance. So if we now increase this one to the -4, see if that helps. Not much. Okay. -5. No. Can squeeze him hard. Doesn't really help much. Unless I have done something wrong here. Because he should be better than that, but I think I did it correct, didn't I? 1 over... Yeah, it should be correct. Okay. What about the others? We have 23T and also 23TB. We can have a look at those as well. 23. Now we're talking. So 15, the accuracy wasn't really good, but 23 did the trick. So yes, you risk jumping into a stiff equation system sometimes. Then you should know what to do. And this list here can sort of help you playing around, test them, check them if that one can do the trick. So for this very brief little equation system, looks innocent, but no, he's not. He's really tough, really tough. Any questions to that one? That's okay. One thing, here I used inline. That is one way to do it. I wonder, I haven't checked this one, if you use an anonymous function. That's another way, should be another way to write a function inside your script without having to use any external files. So we have a function of y as an argument, and he returns y square minus y cubed. Comment of that one. We can try it. No, he didn't like it. Something, I missed a parenthesis, sorry. No. So you can't use an anonymous function with this ODE here. You could use this inline trick, else write a separate function. But I mean, inline here worked quite nicely, so why not? So I believe the stiff equation also something that you will be given on an exercise, isn't that true? Yes. So you're going to fight with this one yourself. Okay, no questions? Then we stop here.